But on behalf of Claire Bowman and myself, again, thanks for inviting us up. We've been having a blast talking to you all. It's really refreshing to hear the really incredible work you guys are doing. So, and I think there may be some pathways that we could use some of that in some of the products we're developing. So a little bit about image engineering. We're located in Curtis Bay, Maryland. That's right outside of Baltimore. We have offices in Las Vegas, Nevada, and Los Angeles. And right now we have about 76 employees, I think. So we're actually growing. Our clients include, I think it's 18 NFL teams. So at any Sunday, if you're watching an NFL game and you see introductions with pyro and special effects like cryogenics, that's probably us. Of course, we do the Eagles too. That's our honor. MLB, NHL, NBA, Sir Paul McCartney, Lady Gaga, BTS, TSO, Rolling Stones, and it goes on. So we have the company is actually in two segments. One is the live entertainment, which is the sports, and also includes the touring people, which are the tours that go out, the rock stars and what have you that go out. So we provide all the lighting and lasers for them. And then the other segment is an engineering division, which is starting to grow now. I started it back in, I guess you can say I started back in '88 when I turned my first ion laser on and was just completely captivated by the beam that came out of it. And so right now that's growing and we're moving more into themed entertainment. So we're building devices and effects for themed entertainment. So some of the special effect engineering projects we're building is liquid and gas flame systems. And you know, some of the work that you guys do could be applicable to this space. We do use actuators. We try to find novel ways of putting flame somewhere in 2D space somehow. And with actuators, we're working on things along that nature. Water effect systems. So we build an array of water cannons and other things that are used probably most like in Las Vegas. We have some there. There's other effects. I believe we have some in SeaWorld now. Is that Texas? That's Texas SeaWorld. Architectural and LEP lighting. We just started getting into laser excited phosphor technology. And that's because we have a big project coming up next year, which wants a bunch of searchlights in the sky, but they can't deal with the amount of power that's required. The old searchlights made by Synchrolight, we have pretty much all of the inventory. 7,000 watt xenon bulbs, and we can put the same amount of radiance up there with about 1,000 watts or less using laser excited phosphor devices. I got a little bit more to say about that too. Entertainment laser systems. So we do our own embedded designs. We also use PLC in some of our other designs for themed attractions. So we do have engineers that do a lot of embedded programming. Show and effect control systems as well. Anyway, this company was a laser light show company, and we started like in 1988. So this is about the birth of the industry. Actually started a couple of maybe 10 years prior to that, but we were like in the introductory phases of laser entertainment when the lasers were huge. And so what I thought I'd do in this presentation is sort of give you the history of lasers in entertainment and how we fit into it and how we expanded into using this technology for additional clients as the technology of making laser light improved. So actually in 1916, Albert Einstein predicted this was possible to have light emission to stimulate light emission to stimulate emission. And it's something that doesn't come to mind very easily to think that a photon going through a system knocks out an electron at some energy state and produces a photon of exactly the same frequency. So you get this light amplification going on. So Albert Einstein predicted that. In 1953, Charles Townes conceived a way for microwave amplification to stimulate emission. This was a maser. Okay, so it's microwave to stimulate emission. So it's not optical light. He won the Nobel Prize in Physics in '64 for that demonstration. And it wasn't until 1960, a number of years later, that Theodore Maiman, HRL, built the first laser. And the first laser using optical light. Okay. And this was built using a synthetic ruby crystal as a gain media. So, lasers need a pretty special material to laser. They have to have a direct band gap. Okay. If you have a direct band gap, you can excite electrons into an upper state, they fall down, and then you can put a mirror on each side and they bang back and forth, and they can stimulate emission in that. So that was the first, in fact, the light that came out of this particular laser was 694 nanometers, which is a beautiful deep red. And we don't use that because it's hard to see. It's pretty dim. But it's actually, you can actually get 660 out of YAG that we got out, and that's pretty deep red too, but it's hard to see. Anyway, this sort of summarizes how it works. You need a special direct band gap material. You excite it, and most lasers are excited some way. They're excited with flash lamps back in the old days. Today, their laser diodes are excited through current or voltage. Okay, so they're diodes. But you excited electrons go up in a higher energy state. They fall down, and they produce a photon of light at some frequency. Now, if you put a mirror on both sides, you can basically take that photon and direct it through, and it's going to knock some other electrons out, and you have an amplification that goes on, and lo and behold, you get this beautiful monochromatic in-phase light out of this material. Some of the lasers that we only had back in those days was YAG, yttrium, aluminum, garnet. Again, it's sort of like a gemstone, garnet, and that it was a suitable gain material. It basically lays in the infrared 1064 nanometers, so you couldn't see it, but you could do a second harmonic generation. It's kind of a magical process, and I had a lot of guys explain this to me. He said, yeah, 2 photons that are low energy makes 1 photon high energy, and that's how it works. So you put a nonlinear crystal in its path, 2 infrared photons go in, 1 optical photon or visible photon comes out, which is 532. That's how it works. So back in those days, you could make really big, powerful lasers with YAG doing second harmonic generation. We started with argon ion and krypton ion lasers. These are big gas tubes that required a tremendous amount of energy. I got a picture to show you where we started. They traditionally took 40,000 watts of electricity and 5 gallons of water per minute to cool them. So they're really big water heaters is all they were. They produced some laser light, but that's the only way you can get some laser light. Helium neon, which was a gas laser, usually lower powers. Helium cadmium was another technology. You can produce this deep blue 442. So there was a lot of schemes back then using 442 nanometer to make heads up displays in windshields of cars. You could put like a fluorescent material in a windshield of glass and then scan on it and make images appear. And the FDA says, oh, not so fast. So you got a laser in a car. And, we're not going to let you do that. So think some other way to do it. Copper vapor. Now, copper vapor was what we call the big gold laser back then. So copper vapor produces 578, which is like a yellowish gold. And some of the beam parts fault these lasers because you get them in 10 to 20 watts. And it was a huge, big, thick beam because it was basically a thyrotron that pumped it. And so the beam had to necessarily be large. And the only problem is you had to feed it copper throughout the day. It ain't copper. You had your little copper pellets that you had to feed this thing throughout the day. So, but anyway, we use laser diodes now. Gallium nitride is really the material of choice for making blue and green. In fact, you can use gallium nitride, and you can make a 6-watt laser in a 9mm can. I mean, that's incredible. You make green too, about 520 nanometers. And the red comes from indium gallium nitride, and aluminum gallium arsenide, indium phosphide. Aluminum gallium indium phosphide. So that's how we get the red. So they're all solid state and they're all diodes. Very efficient. They're all about 40% efficient. So we think the first use of laser in entertainment was in the Goldfinger film with James Bond. Okay, and here Mr. Bond is on a slab of gold and he's ready to be bisected by this orange beam. Well, it turned out that if you really read the story behind this, they brought in a laser. It was a helium neon laser at that time. Just wasn't bright enough with all the lights in the set, so they couldn't use it. So they said, "This ain't going to work. We're gonna have to like Photoshop this thing in. This beam, so that's photoshopped in, but it showed these sparks coming out of out of this gold slab that he's sitting on, and that was like a welder under there. And Hollywood finds a way to do it, right? So Charles Towns had a graduate student, Elsa Garmeyer, and she was at MIT under Charles Towns at that time, and she was doing a PhD in linear optics. And during the time she was there, she noticed that she had optical lasers at the time, most were gas lasers. And she noticed that she could put the beam through various materials and get some really cool diffraction patterns. And she's noted for doing an experiment where she put Duco cement, which is like a cement glass tube, on a pane of glass, and she shined laser light through it, and she got this really cool diffracted image that we call lumina. It's known as the lumina effect, and she's attributed to discovering that. But she was fascinated by the kind of diffraction patterns you get out by putting lasers through it. So she put a little demonstration together, and she went to Caltech as a postdoc. So she went to Caltech to consider, and at Caltech, she formed another project there, which looked at lasers for doing different lighting applications, and she presented I guess it was a presentation at the local art gallery. It had an art display in LA, and she showed all these lasers going through, for Duco cement and going through some other materials. And this guy, he was a filmmaker, Ivan Dreyer, shows up. I think he was studying film at UCLA. He was there, and he saw this. He says, "Oh my God, I've never seen anything like this." So they produced the first company, the laser light show company, called Laser Images. So Garmeyer and Dreyer started it, and they produced this show that they did in planetariums called Laserium. And Laserium was basically, it's usually like rock music or something with the planets, and then you have these laser images going through and doing Lissajous patterns and other kinds of things. So that expands to 46 cities and seen by over 20 million people. So Elsa left that company because she says, I still want to do science. So so she went back, and I think she's still she's a professor. I think she's a professor at a different university now doing nonlinear optics. So that's actually we attribute these two individuals for actually producing the first laser light show. Anyway, this is where we've been. It was hard to do this, to do laser light shows. I don't know who this guy is. I got him off the internet, but he's holding a Spectraphysics 171 ion laser. That is a argon ion laser that produces about 20 watts of green blue. Okay, and that's the size of it. Weighed about 150 pounds. He's pretty strong. And here's the exciter. So the exciter, this is the power supply for it. Basically, had a big bank of these big power transistors that are all in series parallel combination to get the current voltage up through this thing. But this thing needed 40,000 watts of electricity in, 20 watts out, so you can do the calculation, 0.05% efficient. That's all you had. 5 gallons of water per minute, 480 volts, 3-phase, 70 amps per leg is the service you needed. And if you went to a client, you said, "I need that." They said, you can't do a laser show here. So, very fragile glass tube. We still have a couple of these tubes, and they're beautiful pieces of art. If you look at them, glass tube and ceramic. So here's our company that sold the Olympic Games in 1988. And so we did the opening show with lasers, and you can imagine, I think we had 7 ion lasers there. I'm not in this picture. Required 280,000 watts of electricity, 35 gallons of water per minute. That's what you do at a laser show back then. So just to show you where we came from. So since producing a laser light was so hard, you had one beam. So you had to do many things with that one beam. And so you make these huge projectors. This is a projector you slide in your ion laser. And you get XY galvanometers, which would actually draw the two-dimensional images, the amplifiers, beam turrets. So you had one beam, you had to do a lot with it, route it around, you go through luminous glass, you go through diffraction gratings and things like that. So, you know, it was hard to do these shows, and the equipment was big and heavy. And here's, this was in 86. Governor's Island. So this is when Ronald Reagan flips a switch. It sends, these are two 20-watt argon lasers 1 mile across the harbor to illuminate later Liberty after she was renovated. So pretty cool. But you know, it's 2 ion lasers, so it's 80,000 watts of electricity produced at one beam. Technology has been kind to us over the years. Okay, and that's why we still in business, because if we had to do ion lasers and try to get these utilities, it'd be very difficult. So in 1994, the demonstration of a 40-watt lamp pump YAG laser at Stanford University was demonstrated. And this actually was a laser developed for laser surgery. It's green. So a bunch of guys, you know, they figured, well, they went to the company and said, can you make this that we can use it? Take the laser scalp off and all the other stuff, and so they made a laser entertainment industry. And back then, when people saw this, they said, "Oh my God, that's the brightest thing I've ever seen," because that is at 532 nanometers, which is the peak of where your eye can see. So your eye sees different colors at different magnitudes of intensity, and 532 is like right at the top, so it appears the brightest. So you can see this stuff 20 miles away. Optically pumped semiconductor lasers, OPSL, allowed more greater efficiency. So we got to the point where YAG was being used, pumping YAG with either a flash lamp like this laser, or with another infrared laser diode as the optically pumped semiconductor laser from coherent radiation, gave us you know, much more efficient lasers. As I mentioned before, now everything is a laser diode, and we still use the optically pumped semiconductor lasers because the beam is really nice. It's a nice, small, low diversion beam. Laser diodes, right? You know, if astigmatism associated with them, there's 2 axes on them, and it takes quite a bit of screwing around with the optics to get them to look good. Anyway, this is what we do now. We take many individual laser diodes and we stack them this way. We stack them into a 2D grid. And so if you think about this, it's completely scalable. You can scale and make any kind of laser you want now. And getting more than 40 watts at any visible laser before, that was almost unheard of. So right now you can have up to 200 watts of RGB by doing this stacking. All right, so back in 2009, we built this laser. This is a 20-watt plug in the wall, and we believe this is the first laser built in the United States that used laser diodes and one of these OPSLs, which is this it's a green light. So here's a green source, 20 watts, actually 25 watts, 14-inch by 24-inch case, less than 5 or 6 amps out of the wall. So what a difference that made. Green source was this 10-watt OPSL. So this little module here is only this big. You know, it's very small, producing 10 watts of green light. Red sources were being combined 36 of the 200 milliwatt lasers. 200 milliwatt lasers are a lower power because the stripe of it was smaller, so it's easier to make it's easier optically to stack the beams to make a good low diversion beam afterwards. And then blue laser diodes, which were the gallium nitride. Actually, I think those laser diodes came in a passive video projector. So today, that's a 100-watt laser right there. So you have green source is 30 watts, 1 watt, 520 nanometer. Red source is 60 of the 500 nanometer, and source as well. So, you know, you guys are all engineers, you say, how in the hell do you keep all this stuff aligned, right? How do you keep, look at all these have to be aligned perfectly, because if not, you'll have beamlets come out. And so the entire system is TEC cooled to plus or minus like a degree or two. So try to maintain constant temperature. And everything's small. It's small. There's no cantilevers and stuff hanging. It's a very, very small optical assemblies. And everything's epoxy once it's adjusted. And I have to admit that when I look, you look at this thing, and I like I said, I built the first 25-watt lasers, which are 36, where the red lasers were combined. It was hard to keep all that stuff aligned. As you make stuff smaller and more compact, put everything into a temperature controlled environment, you can actually. What I'd like to show you some examples our company did in laser animation. And so 2004, the George Bush people, this is Madison Square Garden, I think it's Republican National Convention. He won the bat signal. So that's 40-watt gag laser doing bat signal. This is Ray Lewis, one of the legendary Baltimore Ravens players. This is the 25. The dance, choreographed dance. So he come out, there's flame pots there. We actually worked with him and choreographed that. Another example, the University of Baltimore. So you can just have these scrolling images on buildings, and you can put people's logos and other things, and you can illuminate various aspects of the building. I'm always doing projection mapping, but with lasers. So this is what the lower power lasers, the lower energy of the more energy efficient lasers allowed us to do. You do the same thing. We did a lot of scanning on ice with that. Pretty bright, pretty brilliant. Contrast is quite good. So remember I told you about the luminant pattern, effect, the diffraction glass. So a number of 2013, the Kennedy Center had this was a 1-month program where they wanted to do, it's called Nordic Cool. And they had this lighting designer coming from the Netherlands, I think. And he wanted us to, he said, I want the Aurora Borealis on the exterior of the Kennedy Center. And said, how do we do that? And we showed him the lumina effect in our lab, in our demo room. Says, that's it. I want to see that projected all over the building. So that's like probably 15 lasers that are projecting that. So there was some movie they were filming in Washington, D.C. at the time, and that appears in the film. Hey, that's our stuff. Then of course you can use lasers for musical acts. Here's an example, the band Perry at the Country Music Awards. So this was the first use of our 25-watt systems we built for the company. Take some looks. So, as far as CDRH is concerned, FDA, you'll notice in some instances these beams may actually touch. But you go through a safety talk with the performers, you say, "Well, don't look up behind you. These are damage for vision," and you can do stuff like this. So this was just when you had the technology, you could actually do stuff with many lasers at once. And this is a pretty epic look. This was our first use of putting lasers in a linear array. And this was America's Got Talent. We did a couple seasons of America's Got Talent. And this is where we use these green laser bars. And it's pretty epic looking because no one's seen anything like this before. We have lasers behind it coming out. Let's get a curtain. You can actually modulate them too. So now we have systems that are full RGB, not just red. Unique wave patterns and effects. Here's another example of kinetic use. This is America's Got Talent again. This is using our full color. And we made these rooms that she walked through kinetically with these beams. That was carefully choreographed. She went straight through the light. We had to practice. Do not put it way to make sure you don't flip it one or two. It's pretty interesting what you can do kinetically. And this gentleman shows interaction of
very fast audition
of an actor with laser light. So he had this like robot thing that he did. There's one scene here. He actually captures a laser beam.
Yeah, I'm good.
This is Radio City Music Hall, and it's like there was no time to practice this stuff, you know. Okay, so here's some more applications. Lady Gaga had the Joanne tour, and just to kind of, emphasize when you're in the entertainment industry, what's expected of you. Okay, and if you're doing technology stuff. Lady Gaga's people came up to us 6 weeks before the rehearsals and said, "This is what she wants. She wants to play a piano that has lasers coming out of it, choreographed to when she plays." So I'm saying, how the hell do I do this? So we had to put in 44 individual RGB laser modules. Each one is a string. So it looks like the strings are light. And then when she played, she could hit an actuator, which would take the beam to one of these actuators and it would come out over her head like this. So you do all kind of chases and other things as well. So we intercepted, she was playing electronic keyboard, we intercepted the MIDI and went directly into our laser control software to do this. So, and it was only 6 weeks. I said, guys, you got 6 weeks, so figure it out. So we were up at Lidditz, Pennsylvania, which is where her staging was done. And I remember going up there and trying to get this thing not to overheat, and saying, how am I gonna get this thing that goes out to Europe? So these are the kind of things that really happen. And the Trans-Siberian Orchestra is another one. We do, this is where our flames, I don't think this is a video. Oh, it is a video. That's our new liquid flame system. So it is a rock group that does Christmas music, right? And if you want to hear Christmas music, a rock group perform it better be more than that. So it's got to be like cool special effects. And so they're always pressing us at the limit to come up with cool special effects. So that's an actuator actually rotating the unit. That's our flame system there. It's a pretty cool show. You think you got your money out when you see something like that. And so here's examples of using lasers with other media. So downtown Baltimore is a power plant building. It was actually a real power plant. They generate electricity and they convert it to office course. And we did video projection, lasers, and pyrotechnics simultaneously in this thing. So that's termination of our lasers on various structures in Inner Harbor. I don't know if you've seen some videos happening. It's on extremely brighter projectors. Yes, there's zero. So this one is Ocean City, Maryland. This is a 50-foot diameter inflatable sphere made custom. And we're going to project lasers and video on it. Do a laser show on the beach every week. We did. These are the first 40-watt lasers I made using this technology based on my phone. And you know, they use it for a couple of years. So if we have metrics, we do this. A lot of people come to the boardwalk and they spend money. And the people that run shops, they say, yeah, do this. Because, yeah, we're making more money. We do this. And so, problem when it's windy. It's a real problem. We have a larger screen than this. It's like 3 times the size. It's called the inflatable tower vision. We have a patent on it. And it rises 175 feet with these 2 cones, and it's 110 feet across. So we project lasers on that. And I remember, in some windy conditions, it's like, gee guys, do we really try to put this thing up? Do we not? Because if it gets away from you, you don't want to own it. It's like, nah, that big thing don't belong to us. We don't know where it came from. Very, very challenging. So back in 2018, this is a Staples Center in Los Angeles. This is a combination of 900 individual laser sources, and we held the Guinness Book of World Records for the largest laser show. And how long did that last, Claire?
Only 6 months or so.
Yeah, 6 months
Yeah.
might be it. So yes, arms racing. Yeah, so we had a lot of these light bars that I showed you that we used, which had the array, and we actually actuated them so they can move too. So there was like 66 of them in here, a lot of other lasers, and yeah, they absolutely loved it. So so we did hold it for 6 months, which was good. So as far as visualization, there is visualization softwares that are people use to actually figure out what this stuff's going to look like. Okay, and here's an example. So this is completely simulated, and depending on these show beams going in the audience, which is kind of like illegal unless you're below class 1, which we'll talk about. But it kind of gives an idea, and you show this to the artist and to the client. They say, "Yeah, that's I want that." And say, "Well, yeah, but we can't do this." What do you mean you can't do that? You can't shine the lasers in the audience now. And this visualization software also allows us to put our flame units and other things, our liquid flame systems, other things. We can drop all that stuff in here and completely simulate the show. And then we can generate the DMX stream that they're going to take on tour with them and say, you're looking at exactly what this DMX stream is going to do. These fixtures are there. And that's how we do it. So we look at it all, we program it, and then we send the DMX stream to out on tour, and they get this. I'm going to show you something physically impossible on this planet as physics exists. This is called laser banding. This was done during the pandemic where everything was remote. So I want to point your attention to these. Like that. How do you make a rising curtain, a laser light like that? Well, what you do is you intercept a horizontal scan from the camera and you sync your lasers to that. So only the people viewing it can see that effect. If you're in real life, you can't see it. We sync it to the horizontal scan rate of the action. So it's called laser banding. And so there's even more compelling looks made from that. Anyway, just a word about safety. Lasers can blind you. And the reason why they can is because unlike a incandescent light source, a laser, because it's monochromatic in phase, incoherent, can be focused down to the wavelength of the light that it's emitting. So, 520 nanometers is a half a micrometer on your retina. And if you put that much energy on a spot, it will vaporize retina. So that's why lasers are dangerous. And so to do any of this, we need a variance from the FDA. You cannot take a laser like this out in commerce. It's illegal. Okay. So 400 to 1400 nanometer gets to the back of your retina. And, infrared you can't even see. So, you don't even know you're being illuminated. So a lot of the early laser injuries where people work with YAGs in infrared, they didn't even think they got exposed because you can't see the light until they get the splashing in their eye. And, so it can be quite dangerous. So there's lots of things we go through to make sure these shows are safe. And one is that you can't do a class 4 laser show. Class 4 is greater than 500 milliwatts. It's got to be 3 meters above the space or the floor that people are standing. 3 meters above and 2.5 meters from where they can put their hands. Okay, so that is so that they cannot. If you think of an NBA player putting his girlfriend, who's also very tall, on his shoulders, they still may be below 9 meters. So that's the thinking. So anyway, you have to be very careful doing this stuff. And you have the variance to actually to do shows out in commerce. So one thing that's required is a human operator is required at every class 4 show. Every class 4 needs a human operator to sit there, observe the laser termination points, and hit the EMO button if something bad happens. So we started talking to people at theaters and other people that want class 4 laser shows, but they don't want a person sitting there. And so we came up with a way of, and it's through the FDA, it's called it's an autonomous system for monitoring class 4 laser light shows. And it uses a combination of technologies. You can install this and you basically follow the variants. You don't need a person there to do it. So there's some So so we're pushing that into some market segments that never see could do this otherwise. So another thing we're looking at is you can actually take lasers and scan them in people's eyes if they're below class 1. Class 1 is when you go over to the supermarket and you scan your avocado, and that little polygon that's spinning, puts the red line on it, that's class 1. The laser pumping on the polygon is not class 1. Probably higher than that. You look directly at the laser beam, it may injure your eye, but since it's being scanned, it's class 1. So there's a direct relationship between exposure time and the amount of radiance that you put in your eye. Okay. And that's because there's a time constant to do biological things on your cells in your retina. Okay. So we do audience scanning, and it means that our scanners that we typically use, galvanometric scanners, can basically go as fast as a couple hundred microseconds excursion. And so it's a millisecond of exposure time across your retina, and which means that you need something in place that can continually monitor the speed of the galvanometers. If they drop below the 1 millisecond exposure rate, it must shut the laser off. And so we do that all the time. The irradiance is only 10 milliwatts per centimeter squared, so it doesn't work that well. You need a dark, smoky room like a nightclub for it to really work. And if you're out on the stage with video and other lights, it's really not very compelling. But and here's an example. So the human blink reflex is 1/4 of a second. So you can blink fast enough to save your eye, provided it's not greater than 2.5 milliwatts per second squared. You can actually blink fast enough, and that's what you typically do with the aversion response. You blink, and it protects your eye. But what if you could have an exposure time of less than a microsecond? Then you could put 2 watts per centimeter squared in your eye. And that's very bright. And well, it's just as bright as the other light, but it's actually it's pretty bright. And it's you don't have to expand the divergence to get the irradiance lower. So we developed a system called the Vertex, and this is the early version of the Vertex. This has a polygon scanner in it, and what it does is it scans at, this was at 4,000 RPM. We now scan it. We have another system scan at 10,000 RPM, and we modulate the beam as it's hitting that polygon. It was some really nice, embedded development there. It was a lot of fun. And so we're going to unleash this product probably spring, and we think it's going to change audience scanning such that it's not going to be this fuzzy, hazy, low-level intensity that you can scan out, but it will be much more compelling and actually compete with other lasers that are class 4 that are over your head. That's the hope. And some of the data that we got now, some of the looks that we're programming, looks like it's going to probably meet that case. And here's an example of that. So this shows our. So in the middle here, you'll see this fan come out. That's from the polygon. And so these other things are class 4 lasers. That's the light bars, called the vector bar. So there it is. Pretty bright. You can do other things with it. You can kind of spread it according to this wide. You can actually scan on the fast. Class is like 5 millimeters. Other the alpha get right effect. So we think this is a way of having some really compelling audience scanning effects, and you can do other things too. Here's like a reveal. So you just get these curtains of light that can open up, and they're perfectly safe to view. You got a person walking through there. Okay, I think this is my last slide. So what do we see for the future? We think lasers are ubiquitous in live entertainment touring. There's no other way to get volumetric light. That's not a way to do it. And unless you come up with a technology, put photons in free space and stick there, there's no other way of doing it. And so we're thinking, with an audience scanning technology that can immerse people actually in the volumetric light is going to be a real plus and give people a different experience. So we're always after like the new look, the stuff that's never been done on the planet before. And so these are the things we're getting excited about. Laser augmented movie theater experiences. This is something I alluded to when I was talking about this operatorless system. So you might see some lasers extending movies. Large scale volumetric displays using mixed technologies, drones, video projection. In fact, I think some of the most compelling uses of drones is when it's a mixed media. When drones are basically used with large scale video projection or lasers or something else, it's something that's unexpected. It's like another element that comes out of something. I think Disney and Universal are thinking along those lines. And then finally, we just started getting into the laser illuminated phosphor development. And I made a couple prototypes. And so here's some views of this thing. Here's a beam that you can change the color within the beam. Okay, this is 36 elements, and each element has its own color wheel. So you can do this kind of thing. And remember, this is plug in the wall. This is not a 7,000 watt xenon. And here's some other examples of that too. One thing you can think about is that, if you made a searchlight that's very energy efficient, you put it on a drone. Basically have a beam of light come out of a drone, that's incoherent and it's safe. Okay, so that's one thing you think about. And we thought about putting lasers on drones. It's like, oh, what's the FDA going to say about this? So the drone takes a beeline, going to expect a place. How are we going to tell the FDA we're going to keep that from hitting people? So we're still thinking about it. So it's there's never an end of ideas in this business. I'd like to end that. Any questions at all? No. Thank you. Yes, sir.
I'm not sure I quite understand what you would have lasers on the drones and the FAA doesn't like that.
Yeah, they're not going to like it. They're going to say, okay, you got a laser on the drone. Where's it pointing? Well, it's sort of like pointing at another drone. So suppose you're going to make a kinetic sculpture where you connect the dots, right, with a coherent laser beam. They're going to say, what's going to keep that beam from, a malfunction from keeping that beam hit somebody on the ground? What if you lose control of that? Is the software sophisticated enough, the drone that says, I'm not in the right place where I am, I'm going to drop, and I'm going to shut the laser off. So I have to then write up extensive amount of paperwork to the FDA and explain to them how this is going to work. Say, look, this is it, the software, basically, the drone knows that it's not in a good place and it's going to drop, or what if an air current or a wind comes and blows the drone for it tilts? Then you almost need the laser on a gimbal or something to keep it steady, keep it in the right place. But you have to write that all up to the FDA, and then the FDA has to review this. It takes a year to review this stuff. So I don't know what to do there.
Would it be any safer to have you could put mirrors on the drones and then let the laser is coming from the ground so that
you could do that too. We thought about that.
Yeah.
We thought about that. You would need some kind of tracking software that's fail safe. So if the drone is positioned this mirror, suppose you have the mirror on a gimbal. It's kind of like doing this. It's picking this beam up and taking the beam over here and then taking the beam over here. It's like, how am I going to make sure that that mirror is not going to put the beam in a bad place like the audience is? So you have to think about that. How do you protect that? So they do not know. FDA got involved because when lasers were starting to be made back in the 70s, rock groups started taking them on tour with them, like Blue Oyster Cult. Okay, and they had injuries. They basically, they hit a mirror ball with it. They said, well, let's put a laser on a mirror ball. That looks really cool. All these shards coming out. Well, it wasn't class 1. It was like class 3B or something like that. That's where they got involved. They said, you can't do this. So it's a good point. I think if we could, and that's why I was thinking about laser reduced phosphor. Like, you have almost a hammer beam. Now, we did some tests. It's like, you can't see it that well. You know, you can't see it that well. My brother said, I don't know if I'll put any more money in this, John. You guys hear this all the time, right? Research, oh, write paper and we'll wrap it up. So, yeah.
I was gonna ask, like, when it comes to like the power drop, because that seemed like to be a common theme with the history that you're getting a lot more efficient with the lasers.
Right.
Is that something that you expect to continue to improve, or are you hoping that it's more improvements from things like batteries or other power sources for lasers?
But I think as far as the optical power per square centimeter or cubic centimeter, I think we're probably at the limit. Because you just can't get that much energy out of a confined space. Like, I mean, gallium nitride, you get to a different crystallographic plane and maybe get more efficiency and make a laser, but not much more. So I think as far as the space to make lasers, the cubic centimeters to make laser light, we're probably at the limit of what we can do. Unless you make big bars, you make stripes, you can actually add laser diodes and get the stripe longer and longer and longer. So, but what happens when you do that? Well, you have an axis that diverges like crazy, another axis that diverges much. So one's almost like single mode. So it's like 1 micron by 3 centimeters. Right? So 1 micron, that's a nice little tiny, stripe, but the 3 centimeters is widespread out. So you have to continually expand the beam to get the divergence down. And they like ameliorating in this business. So by the time you get a laser that's doing 20 watts because you need a real long stripe, you put the optics in there, you have a 14 millimeter diameter beam. It's like, all right, well, I got to move that with a mirror. All right, what mirror? You guys know mechanical stuff. It's like, can I move something that's that big as a piece of glass? And well, it hurts.
Yeah, it's
Hard. It's hard to do.
I guess also like when it comes to that automated solution you were mentioning about how you wouldn't need somebody in a theater. Are you tracking that based off of knowledge from like stuff like actuators, or are you using some type of vision system?
It's got to be a vision system.
Okay.
It's got to be a vision system. It's got to be sending out telemetry. It's got to take logs. It's got to shut this thing down immediately. It's got to notify personnel. But if it works, they just don't want it, in an environment like that, they don't want a guy to go up there and change the light and leave his ladder in front of a projector or something like that. Projector, laser hits the ladder, diverges off, it's the person. They also don't want people walking on the back of their seats or throwing stuff in space, the zoning above them, because that would be bad too.
Right.
So I did all kind of tests. I mean, you could throw your cell phone. In fact, I've thrown my cell phone up in front of a beam. It's like, it really doesn't reflect the beam. It's a diffraction pattern. That's actually pretty. Easy to do. Take a laser, hit the surface of your iPhone. It's fraction. If I had to do all the experiments, I'd say like a silver dollar and flip it up there, and a mylar balloon and mylar confetti and all this just to show these people saying, well, a mylar balloon is like a curved surface. By the time the beam hits it, it's spread out, right? So, it's below class 1 by the time it's spread out.
Right.
And you say, all right, how'd you do it? And what's the distances and blah, blah, blah. So you have to do all these experiments. And so we get to the point where we say, okay, finally, all right, if you do this, 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 and this, you have variance.
Right.
But follow all these rules.
That makes sense.
Yeah. So we're kind of excited about that, and they open up a whole new space. People don't like to have governmental agencies attached to it. Yeah, this laser emission, this laser stimulated phosphor is, there's some laser stimulated sources you get out and they're class 3D. They get a variance to use them. Because you put everything under one lens, right, it's really bright stuff. You gotta be 100 feet away from it, was class 1, so therefore you need a variance. So when you get a variance, what's a variance tell you? Well, you need an LSO on site to run this thing. And it's like, these guys that run searchlights, they don't have to hire somebody to sit there and make sure they sticks their face in this thing.
Right.
So you gotta come up with compelling technologies that are safe. You know, that's the whole bottom line.
Makes sense.
Yeah. People like go out to see a show, you don't want to hear anybody. Not want to hear anybody.
Yeah, definitely.
Thanks very much, guys.
Thank you.